All right, we're live. Okay, hello everyone. Thanks a lot for coming, for joining this space. I just wanted to quickly introduce the participants. So today we have Adam Beck, the CEO of Blockstream, and Andrew Pelstra, the Director of Research, Abdel Vakta from Starkware, Head of Ecosystem and Exploration Projects, and me myself, I'm the engineer from the Exploration team. Yeah, thanks again for joining. Today, we really wanted to talk about simplicity language and its way from research paper to find a liquid mainnet, its future, and the synergy with the Stark technology. And we'll try to fit into roughly 45 minutes, and we'll leave 10 minutes for answering questions, which are, by the way, anyone listening can post, so we will see all of them. Okay, first of all, congrats with the mainnet launch. Simplicity was activated on Liquid Mainnet last Thursday, so it's a huge milestone. Super excited. Honestly, so we haven't yet deployed anything to mainnet yet, but we will soon. So yeah, also excited about
you'll
this.
have the first Stark proof-based simplicity spend coming up, yeah?
Yes.
Hopefully,
yes.
yeah.
And this time it won't be a toy one, so it will be a proper one. All right. I guess let's start from basics. And for those who do not really familiar with the tech, what is simplicity? So how can you describe it in a couple of sentences? I guess it's a question.
Sure. Yep. So simplicity is the way that it fits into a blockchain, right? Is it basically it slots in where right now Bitcoin script is. So in Bitcoin today, there's a scripting system that's built into it that is fairly limited in what it can do. It's designed basically to check signatures. So it can obviously check that the transaction is signed with the key that's embedded in the address. It can check various time lock conditions. It can check hash preimages like in an HTTP kind of thing, and various combinations of these. But despite being so limited in being that it can really just do those three things and not a whole lot else, it's quite difficult to reason about Bitcoin script, and it is quite hard to understand in detail how exactly it's going to behave. I've been working on Bitcoin for over a decade, and even so, now it's only every year or two, but somebody will notice some obscure corner of script and some weird behavior that nobody, to the best of our knowledge, that nobody even noticed before. And the reason is the script is implemented in C++, and it's defined by what the C++ code does. And its semantics are that you've got kind of this what's called a stack of opaque blobs that you're kind of shuffling around and duplicating and manipulating. And every so often you interpret one of them as a signature or a number or a Boolean or whatever you need to interpret it as for that moment, and you do some stuff with it. So simplicity slots in where that is. And simplicity, unlike script, is not limited in any computational way. In script, you can only do a little bit of arithmetic and do a couple of specific crypto opcodes. In simplicity, if you can compute something in a finite amount of time, you can do it in simplicity. And not only can you do it in simplicity, you can, given the simplicity program and what's called a witness showing that you did the computation correctly, any validator can scan through it extremely quickly and determine exactly how much memory and exactly how much time it's going to take. And they can do this in time proportionate to the encoded size of the program. So simplicity, unlike script, there's many differences, but unlike script, it's not an opcode language where you run like one thing after the other, shuffling all these stacks things around. In simplicity, you describe your program as a function, not quite a pure function because it's allowed to abort and it's allowed to kind of read stuff from the witness that the users kind of provide at a spending time. But you kind of build up this function by starting with these two simple functions. They both essentially do nothing. One of them takes its input and throws it away. The other takes its input and passes it through. It turns out you can build anything, any function, any computation you might do, you can build by combining these in one of these 9 possible ways. So simplicity is defined as these 9 combinators. And so you put that together, you can express any computation where you do the same computation multiple times. You only have to encode it once, and you can kind of refer back to it multiple times. And so you don't have looping per se, but you can have this like enormous branching tree of simplicity executions, which when encoded is just a single branch. And even if you're executing code in one branch repeatedly, it only appears once. So you get, so tying this all together, simplicity is a language defined almost in terms of like pure mathematics and like the most basic building blocks of computer science. So we have a formal specification. It's not defined by what the C++ code. It's defined by, I guess ultimately it's defined by some C code, but it's very simple C code, which is implementing implementing the language, which is also defined in the ROC theorem proving assistant. We might be defined in Lean. We haven't done it in Lean yet. It's written in Haskell, it's written in Rust, it's written in several other languages that have strong type systems and are designed to be easy to reason about and easy to produce machine checks that you're not doing crazy stuff. We have all those nice, like what's called formal specification of the language, okay? And we have full expressivity. You can do anything at all. So unlike Bitcoin, where you start with like, it can't do anything and it's still overwhelming. It's like, how are we going to add stuff to it? Like very carefully, right? With simplicity, we start with being able to do anything. And the questions of adding stuff become, well, what operations are people doing that are currently very slow? How do we speed that up? So things that today, rather than talking about how in Bitcoin you can't do X, so what are we going to do to make X possible? If we had simplicity, we would say, well, X is very expensive. Can we make it cheaper? You know, how can we slot in some special purpose code for X, which is a great difference, right? Because it means that one issue with doing large changes that we don't really know how or if anybody's going to use these things, right? So then we debate endlessly, like, should we do one of these 5 different covenant proposals? Nobody knows because nobody's doing them. In simplicity, well, you can do it. It might be expensive, but if you really want to do it, you're going to pay the cost. And then we can step back and say, well, maybe people shouldn't be paying this high cost and we shouldn't be using so much blockchain space. And that's you know, this is what people are doing. Let's bless that by making it more efficient. And then we also have this compact encoding scheme for simplicity. And finally, for users, because simplicity itself is formally specified, that means that when you write programs in simplicity, you can write a formal specification for those programs, and you can prove, in principle, you can prove that the code that you're running on the blockchain exactly meets your specification, and that it's not going to do some surprise thing where it's possible to steal the coins by, you know, calling a function in a certain way, or it turns out you can't spend the coins because your witnesses are way bigger than you thought, and you can't get a fee rate high enough, or, you know, any of the other number of surprises that have happened in other systems where people try to just extend Bitcoin script. So that was more than a couple sentences, but I tried to, throw it all into.
It's great. It's great. Yeah, it covered like a lot of questions I wanted to ask. But yeah, from what I learned, like from the interview actually with Russell O'Connor just a couple of hours ago, is that he started working on simplicity almost a decade ago, right? And the white paper came in 2017, where actually it's what you just mentioned, right? So simplicity is addressing kind of 2 large things: the limitation of Bitcoin script, and especially after a bunch of opcodes were disabled by Satoshi, right? The multiplication, the concatenation, and so on. And at the same time, the issues of the EVM. So it's explicitly pointed out in white paper because it came after Ethereum launch in 2015. And specifically the hardness of doing static analysis, right, of the Turing complete language. And in simplicity, as you just explained, right, we always know that the program would terminate and how much exactly resources would it consume, worst case scenario. So yeah, that's pretty cool. It's also interesting how the history of simplicity is somewhat similar a bit to the history of Caro in our ecosystem. Do you think, Del?
Yeah, absolutely. I see a lot of interesting analogy actually. Like first of all, for me, the common denominator of those two is this idea of building from first principles and start from a design goal and say, okay, what do we need to do in order to achieve that? So in our case, the design goal was to be extremely zk friendly, so extremely efficient to generate Stark proofs. And unlike most of our competitors, we did not want to transform the EVM to a zk VM because we knew from the beginning that it was not zk friendly. So we designed a full virtual machine and proving system and high-level language from first principle, which is the same for simplicity here, to have more expressivity, but in a more controlled manner and still have the safety. And yeah, I was interested maybe to hear from Adam about the flaws that you see in the EVM world and all the DeFi hacks and so on, because I saw you tweeted quite a lot about the DeFi hacks on the EVM world, and how do you see simplicity trying to tackle this and to avoid the same kind of mistakes when it grows and as an ecosystem of applications?
Well, I mean, I think it's designed to be verifiable. So I recommend people listen to Lisa's discussion with Russell. That was quite interesting. But basically, simplicity is a verification language, whereas other blockchain languages are repurposing, I don't know, like virtual machines or making brand new virtual machines that are a bit quirky. And it's a known factor that, if you're doing programming and you've got different pieces of software that are talking to each other over the network, and that's kind of what these general purpose blockchains with state and race conditions do. You have a form of language, which is the machines are speaking to each other in a language, right? And it's a known factor that gets extremely complicated. There's a field of study called language security, and it basically shows is like, the reason that people have been continuously negatively surprised about the impractical security of network computers for decades is because language security is harder than people's intuition suggests it is, and yet what they do to deal with it is they just keep doing more of the same, and of course the outcome is the same, right? So if you want to avoid that, you do something different. And so I think the point here is you can, with simplicity, you have got formal specification, as Andrew was saying, and you can use tools to prove predicates about it. So I think you had already explored with Starkware that you can, get a proof of how much memory it's going to use, how much fees it's going to use, what the verification time is going to be for any program, and do that, verify what that's going to be quickly, linearly with their code size, right? Whereas the general Turing machines, that's not the case. You got this concept called the halting problem, whereas you basically can't know, right? It's like sort of computer science theory that it's unknowable whether a program will even terminate, never mind how long will it take to run, right? So yeah, in a narrow, specific, hard-coded, simple case, yeah, maybe you can predict it, but in a general case, you can't. So simplicity is making things simpler by being verification only. So it's, it doesn't have to run the program. I mean, there's some simple examples like, so Russell was saying sorting, right? So if you were to use a virtual machine and just take a list and sort it, and then check that the output is they're the same. But the simpler thing to do is just verify, send the list and verify it's sorted, right? That's a lot cheaper. It's a ON rather than O-log-N or whatever the best sorting algorithm is. So there are lots of things that are fantastically easier to verify and safer and more linear and more predictable than they are to actually execute. I mean, factorization being one, right? You can prove the factorization of some enormous number and you'll be here for thousands of years trying to factorize it if you don't know it, right? So, so I think that helps simplicity. The formal verification helps, and because you've got the formal semantics that can be imported into a proof assistant, you can potentially make some predicates you care about. Like the only way this you know, the money in this contract can be spent is like this. And you could prove that's true, right? And that's an important factor, because that is the kind, exactly this kind of thing that keeps tripping people up. And that's why, you know, most of the, you know, the big VM-based blockchains are losing billions a year. And, you know, that's not good. It means that you can't really use them in practice, or you can't, you know, scale their use.
I'd like to build on that a little bit. So yeah, so there's and kind of an even stronger analogy between Cairo and simplicity here, which is about this being a verification-based language. Simplicity is used to verify a computation. So as Adam was saying, something like EVM is Turing complete. So like you could, in principle, you could write an Ethereum contract that like checks whether the gold-backed conjecture is true, and then write some code that just like spent the transaction and just throw it over the fence. And then everybody on the Ethereum network would see your transaction, and they would have to verify whether the gold-backed conjecture was true up to the gas limit that you provide. And then we've kind of exhaustively checked that it's not. So you'll run out of gas, and then that it's not true up to any gas limit that you could fit onto the Ethereum chain, I should say. We don't know for infinity, right? Or you could try to factor an enormous prime number by just like trying every value. And again, you write the code to check, and then you write a transaction which runs that code and throws it over the fence. And you don't need to, as a person making the transaction, actually do any of the work yourself. Like in principle, you could just throw it out there. And as long as you're willing to pay for the gas for everybody else to do it, you can do it, right? That's silly. And it's silly that even needs to be possible. And in Cairo and in simplicity, it's just not possible, because what you put on the chain is not instructions for everyone to do the computation for you, so much as it is a transcript of your own verification. So if you have a simplicity program that checks a gold-backed conjecture up to some certain height or whatever, your program will be required to include a witness that you checked it up to that height. And if there's no witness that you can produce, then you just can't produce it. I mean, you stick an invalid witness there, I guess, and then validators would see it and throw your transaction away immediately. And here's where it's important that validators can quickly check what the resource bounds on your transaction are, so they can quickly throw it away. But you can't produce it. But there's another source beyond Turing completeness of uncertainty, which is that in bare EVM, you can write a program that even if you execute it and you confirm on your own that it's legit and it will pass and it should work, that program has access to all manner of state and so forth. This is either state from the blockchain. You can like look up block hashes that are recent enough and that satisfy certain depth requirements. I think there's some sort of random number input that comes from a block hash and so forth. But then also directly in EVM programs, you have this rich statefulness. You have this key value store that you can access. You have local variables in your own code that are local to your code, but actually every validator has to maintain this giant thing. You can look up values from other contracts and so forth. And when you create the transaction and publish it, between you publishing the transaction and that landing on the blockchain, that state might change. That state depends on other transactions. It depends on what order your transaction appears in relative to other things. And so that means that even if you're writing code that computationally you're able to reason about and that you've done all the work to make sure it's legit, there are places in this rich statefulness model where even in principle, you cannot know exactly how your code is going to operate. And in both simplicity and in Cairo, or in any zero-knowledge proof system, that's not the case, right? You can't, in a zero-knowledge proof, you can't say, well, I'm going to prove that this statement is true, but like part of the statement involves like reaching outside of the proof into real life to like check what this value is at the time that the person is validating it. Like you just can't do that, right? The way these proofs are designed, all of their inputs need to be committed to upfront. And this has clear benefits from the perspective of, can you reason about your code? Can you be assured of its behavior and so forth? But it also has clear usability difficulties that I'm sure you guys have encountered with Cairo, where in EVM, it's so easy to just kind of like grab a value and say, whatever this is right now, let's just kind of roll with it and write code that does so. And yeah, we're writing code where like people reorder the transactions, you know, surprising and unpredictable things might happen, but that's fine because probably the result is going to be something that's okay. And when you're working in Simplicity or in Cairo or in any zero knowledge proof system, or really any system where you're verifying a computation and you need to have all the witness data up front, then that means that when you're creating your program, you need to think about where that witness data is coming from. If you have multiple people manipulating the same data in some sense, you have to define an ordering for their operations to go into. And you wind up in a situation where you kind of naturally are drawn to having coordinators and stuff, which it can be a frustrating trade-off, I guess, is what I'm saying. So there's a good and a bad side to this, I guess, is where I'm going. The bad side is, as I said, that if you're trying to do something that inherently involves manipulating a whole bunch of state in a well-defined order, then that can be difficult to do and you might need some sort of coordinator. Although better that you have some sort of coordinator than that you are just like letting the blockchain do whatever it does, and then now your coordinator is actually some like cluster of MEV. But the good side of it is that when you're designing your protocols, it means that the path of least resistance is to design something that doesn't require this kind of like heavy ordering requirements. You want to step back and design your stuff in a way where, to the extent possible, all your heavy computations are pure computations. And that means that rather than writing code that is inherently kind of, you know, well, MEVy is the word that I'm looking for, code that inherently changes its behavior based on the specifics of what transactions go into the chain and what order, you wind up being encouraged. The path of least resistance, rather than doing that, is to do things in a much more rigorous way.
It's like self-modifying code, or I don't know if you guys ever heard of this game called Core Wars, and the idea was two programmers would have to like modify the code and try and attack each other's code, and the winner is the one that, you know, crashed all other people's code by executing invalid instructions. I mean, executing an Ethereum contract with all this state and reentrancy is basically like a game of Core Wars, and of course, you know, there's some smart people out there who will find a way to separate you from your money, right? So,
you know, I have an IRC log from you, Adam, in 2013 or 2014 in Bitcoin Wizards, bringing up Core Wars and saying exactly this. So.
This is the funny thing that you know, what we're seeing about Turing complete VMs is, it was obvious before they did it, and people told them that, you know, this is not going to end well, but they didn't listen, and so here we are.
You mean
right?
Vitalik did not listen, or like?
Well, I mean, actually, that's a story, but yeah, what's his name? The guy that is now with Cardano, Charles Hoskinson, was the CEO of Ethereum, and he asked me in a chat, you know, some questions about, you know, UTXO versus what have you. And then because it was elaborate, he said, "Oh, can I call you?" So I was like, "Okay." And then there were like a dozen people on the call who were all the Ethereum tech guys asking me questions, and I just basically gave them a elaborated version of what we're talking about. So that's a bad idea. Bitcoin has UTXOs for a reason, I think. You know, there's no design document, but you can think about it if you know about distributed computers and network race conditions. And so it's going to be race condition prone. I wouldn't do that, etc. And you know, they did all of the things, right? So anyway.
Interestingly, Charles went back to UTXO for Cardano. Interestingly, so
well, maybe he learned that they didn't. I don't know.
Anyway, they were actually inspired. Yeah, sorry, they were inspired by simplicity in Cardano. So the language is partially inspired.
Yeah. Well, I mean, I think the other thing that we didn't talk about with simplicity is that it's very low level. So it's kind of like microcode, or it's sort of below machine instruction size generally, right? At the base level, right? And so you've got these 9 operators that Andrew mentioned, and they are enabling you to. They've got very simple and defined semantics. So basically, like you know, AND gates and things, but with logic and predicates and concatenation and a few basic operators. And using those, you can implement a 32-bit adder. Using those, you can implement, you know, multiply. You can implement modular mathematics. You can implement elliptic curves. You can implement SHA-256, and that's exactly what they did, right? And then, because that gets a bit expensive to verify if there's a very large program, then you have the jets, which are basically optimized versions of that are not written in simplicity, but written in formal C. And then you can prove that the simplicity semantics for SecP256K1, the library, are the same as, you know, the C version. And for some of these things, we have actual proofs that Andrew and Russell and others worked on, and that's actually like a big part of the time consumption. But it does mean that you can get the efficiency, and so when you're, you know, if so Andrew mentioned the idea of, well, if people use something frequently and it's heavy, then you can make a jet so they can speed it up, right? But interestingly, it doesn't mean that you change the semantics or that you personally even need to upgrade. It just means that, you know, it'll be more efficient if you do.
Yeah.
So it's a little different to a soft fork, right? So the soft fork, you're changing some behavior, or you're adding some new behavior. Here you're not. You're just making the existing behavior more performant, right? So, so I was sort of talking about this loosely as the last soft fork, because people like ossification in Bitcoin, and simplicity, even though it's, you know, in the liquid context, it started in a Bitcoin context in 2012. And I think Russell technically has been working on simplicity for 9 years and a month or two.
Yeah, that's super interesting. By the way, there is another analogy here when it comes to the JITs and optimization. We have something similar in Cairo as well. You know, Cairo is like a CPU with some polynomial constraints, and you can have some basic operations. And we also have a concept of built-ins for heavy operations that are like the equivalent of building a coprocessor for a certain operation, like, for example, a hash function or something like that, to make it more efficient. So it's exactly the same concept. So yeah, interesting.
There are a lot of similarities between ZK world and the simplicity world. Actually, so speaking of jets, so I know there are also introspection jets, right, that allow you to get access to transaction fields. And I wonder, so if I haven't looked like a lot into that, but do they enable covenants and recursive covenants specifically? And to what Andrew you said already, so can you have state actually on Liquid with simplicity?
Yep. So there are so we do have transaction introspection, and the way that this works is that kind of underlying, we have these special jets that give you access to transaction information. And as Adam said, a jet typically is something specified in like the ComCert verified C subset of the C language as a pure computation that was written in simplicity, but we made it more efficient. And actually, there's a bit of a subtlety here where these things are not, your specification is not written in simplicity, but in a slight extension of simplicity that has these objects called primitives that are allowed to reach into the transaction context and pull things out of there. And you're not allowed to actually write primitives into simplicity. The only way to access them is through these special jets. But I'm getting way in the weeds there, but I just want to be technically correct here. But to answer your question, yes, we have transaction introspection of all parts of the transaction. And so this does enable covenants. You can enable state this way, in the kind of the covenanty way, where you have a tap tree, right, which is a commitment of all your different code branches. And one of those branches, say, is just like an op return and a whole bunch of data. And you're going to store data there. And your covenant, what it does is your simplicity code looks at the data that's living in the tap tree beside it. It does whatever processing that it needs to. And then it writes out its own code and the modified data, whatever the output is. And it says the output of your transaction must be this blob. And so in that way, you can do a series of transactions which update state. And this is kind of the kind of standard construction for how you work with state in a UTXO-based blockchain that has covenants but does not have any global key value store. And the benefit of doing things this way versus having a global key value store, right, is that for a validator, you retain this property that when the validator sees a transaction, all the data they need to validate the transaction is there in the transaction. So you can do it in the UTXO model. You can do it if you're using U3XO or something, you can in fact do it with no state whatsoever on your system. You're just like you're receiving a series of transactions, doing a bunch of pure computations and outputting them, which is much, much more predictable and easier to reason about than a system where you're maintaining this giant database and you're doing updates to that database. And even if you're doing them always in a fixed order based on what's coming from the chain, it's still quite difficult to predict the performance properties and how your system will behave with this blob of data that might not necessarily be checksummed and possibly could be changing out from under you and so forth. So yeah, you can do covenants. There's some more interesting things you can do though, which is because in simplicity, well, not more, there's some similarly interesting things you can do, which is, for example, you can define any SIG-hash mode that you want. So in Bitcoin, I guess in theory, you could do this with Bitcoin and enough transaction introspection opcodes and checksig from stack, all of which are in simplicity. But what you can do is rather than signing your whole transaction or signing your whole transaction except the outputs or except the inputs, which are the things you can do in Bitcoin. We have a flag where we set what's called SIG-hash modes. So when you sign a Bitcoin transaction, you choose upfront from one of, I think, 4 possibilities of which parts of the transaction you want to sign. And the parts that you don't sign, third parties can manipulate after the fact, which sometimes is useful for multi-party kind of things. But if you want to do something outside of those 4 sets, like in SIG-hash any prevout, which the Lightning people want to do, where they want to sign a whole transaction except for the specific input that they're spending. And the idea is that they get a rebindable transaction, where you have this backup transaction, which is good for your current state, and then you update your channel state, and then the same transaction can be just pasted on top of the new state and the new state, and so on, right? You can do that in simplicity. And it is pretty much just as easy as doing an ordinary signature, where you use the transaction introspection opcodes to grab all the parts of your transaction, except for the specific input that you want to sign. And we have some jets built in that are designed to make this easy to like grab all of the outputs, for example, at once and just get a hash of those and grab all of the information about each input. We've got jets to help producing these different SIG-hash modes. And so you can implement SIG-hash any prevout in simplicity. And something one interesting consequence of this actually is that when you're proposing something like SIG-hash prevout, you could in fact produce a simplicity code, a simplicity implementation alongside your reference implementation. And that simplicity implementation could act as a formal spec. Say, here is the model that this C code or C++ code is supposed to meet. And obviously checking that the C++ code matches the model is itself involves a lot of informal, like hand verification kind of work. But if you can convince people of that, then the simplicity code, you can get static bounds on its behavior and like prove all sorts of things. So that's kind of cool. But where I want to keep going with this is that you can do one better than just signing, arbitrary parts of the transaction. You can in fact sign arbitrary functions of the transaction. So an example of what you can do with this is you can have a transaction that signs all of your inputs and outputs, except that it allows you to add it allows you to manipulate the transaction in some limited ways, as long as you keep the fee rate within a specific range. So you could create a transaction where a third party or your counterparty can extend the transaction, but they have to keep the fee rate constant so that they can't like sync your transaction by loading a whole bunch of data but not paying for it. And you can do even better. You can have that fee rate be a function of the age of your UTXOs, where you use a time lock based, like a series of time locks, where you say the older the transaction is, the higher the fee rate that's allowed. So then you can have a kind of an untrusted or a semi-trusted wallet that's allowed to provide extra fee funds, and have it so that semi-trusted wallet is able to bump your fee rate, but only up to a limit. It's not allowed to just like immediately throw all of your money into fees, which obviously would get your transaction confirmed quickly, but you don't want to do it. Instead, as your transaction fails to get confirmed, it automatically is authorized to add more and more fees. Meanwhile, your cold keys that like are handling the real money, they don't have to be touched, right? You produce a transaction once, you put your keys back in cold storage. So there's all sorts of possibilities here where you combine transaction introspection and arbitrary computation. And you can get these really cool constructions that go a fair bit beyond what we think of when we think of covenants.
I have a question for you. It's super interesting because most of the use cases that you mentioned are being explored right now in the context of opctv and op-checksys from Stack. So would you encourage people to actually also explore them using simplicity? Because if, as you explained, you can go even further and do more advanced stuff that you would be able to do with those opcodes. Yeah.
I mean,
How is Liquid like being as a sandbox for Bitcoin in a way? Sorry to interrupt.
Well, it already was a little bit in this. Historically, a number of opcodes were implemented on Liquid first, or variants of them that got improved, and then with the covenant type opcodes, for example, Sanka implemented APO using checksys from Stack and Cat, and it's like about 200 instructions, but it shows equivalence that you can implement it. And of course, with simplicity, you can implement a lot more things and more efficiently than that, right? So you could actually, use simplicity as a tool to evaluate and try out what it's like to program with a bunch of different covenant opcodes, right? Implement them in simplicity and then try using them in Liquid and see how it goes in practice, right? Because I think sometimes you don't really get a true feel for something unless you use it for real.
One caveat I'll add. So the big news of the day, of course, is that we launched simplicity on Liquid, right? Which is awesome. This is a real network with billions of real dollars that are in this network, and so that's super exciting. But for the purposes of somebody proposing opcodes for Bitcoin, kind of a limit, if you will, that you'll run into is that Liquid transactions are actually structured a fair bit differently than Bitcoin transactions. We're still in the UTXO model, and we're still using scripts and prior to simplicity and an extension of Bitcoin script and so on. But Liquid transactions support multiple assets natively. They support confidential transactions, which means that all of your amounts, rather than being explicit numbers, are actually cryptographic commitments to those numbers with an attached zero knowledge proof that they're all within range, they're not going to overflow, and that they all add up. As a consequence of that, your fee output, in Bitcoin, there's no fee output. This is kind of a scary thing, but the network fee that you attach to a Bitcoin transaction is just you add up all the input values and you subtract all your output values. So if you are defining a Bitcoin transaction and you forget to put a 0 in your output value, well, guess what? You just sent 90% of your coins to fees. In Liquid, it's a fair bit safe.
Maybe there's an argument for Bitcoin having explicit fees.
Yeah, I would kind of prefer that. I mean, it's extra bytes that technically aren't necessary, so I see why it's not done. But yeah, I feel like at least on the encoding that you use when you're talking to wallets and stuff, and maybe on the peer-to-peer layer, you could add this extra byte or something. Yeah, there's a good argument for that. But in any case, in Liquid, you have this. And so a lot of simplicity code that thinks about fee rates winds up being different on Liquid than it will be on Bitcoin. So what we are working on kind of behind the scenes, hopefully not behind the scenes sooner, fairly soon, is now that we have simplicity loaded onto Liquid, we're looking at what would be involved in getting simplicity. How would simplicity on Bitcoin look different? And it turns out the answer is not. It's simultaneously more than you expect, but also objectively not a lot of work. And we've made a lot of progress towards that. And so over the next 6 to 12 months, say, we're looking to have a branch of Bitcoin that has simplicity on it. And we think that we won't have too much trouble finding one of the kind of reckless signets that are out there, Mutiny Net or one of these smaller things that would be pretty excited to have simplicity there. And then you have kind of the best of both worlds here, where on Liquid you've got simplicity on a real network with real money and with Bitcoins, because Liquid is a sidechain of Bitcoin, right? So you can move Bitcoin over and back. And then if you want to be working with simplicity in a pure Bitcoin context for the purpose of prototyping new extensions to Bitcoin or just reasoning about your Bitcoin code or whatever you're doing, then you'll also have that opportunity, obviously in a test network context, and in probably kind of a crazy test network context. But then that's, to answer your original question, I would say that's the baseline that you want to be working from if you want to do stuff like implementing new opcodes in Simplicity and in Bitcoin. With a final counter caveat that for pure computations like opcat, you can implement those in pure Simplicity. You don't need you don't need a reference to the blockchain. You don't need you just need some way to kind of model the Bitcoin script stack engine in Simplicity, and then you write the Simplicity code, and you can do that with the 9 basic combinators that are printed. Actually, they're printed on the back of my shirt. It's a little too early for me to take it off, but you'll have to trust me that we've got all the combinators printed back there. And so for opcat, in fact, you can go to our web playground, and we have example code for specifically that. So you can go to simplicitylang.org. I won't check. I'm sure it's there. Simplicitylang.org. Find our web IDE or our playground or whatever it's called today, and we have an example program that implements opcat in Simplicity HL, which compiles down to Simplicity. So for some stuff, for pure computations. And it is funny that cat is a pure computation, given all the crazy things it does, but that's Bitcoin. For pure computations, you can totally use Simplicity on Liquid and prototype stuff today. So.
Speaking of cat, I have a question for you guys, because let's say at some point there is a discussion about integrating Simplicity to Bitcoin L1. Are you worried about the same kind of controversial elements that opcat is receiving, like as in, for example, enabling all possible use cases, even some use cases that people don't want and so on? Because effectively you could build like zk rollups on top of Bitcoin and any kind of applications on top of Bitcoin through Simplicity. How do you see that?
Yep. So so similar to when we were talking about statefulness and requiring an order in your programs and stuff, right? The idea behind Simplicity is that by nature of being a verification language and being formally specified, it encourages users. It means the path of least resistance to do cool things is one that doesn't invite MEV to the extent that other approaches would take. And so absolutely, we're going to get pushback on adding Simplicity in the same way that we add cat. And the question in my mind is, well, maybe you're a full 100% ossificationist, okay, and we shouldn't extend Bitcoin in any way to enable any of these new use cases, or at least we shouldn't do it soon. Well, Simplicity is not coming out on Bitcoin soon, okay? It's not going to be here this year. It's not going to be on Bitcoin next year. But suppose you think we should never extend Bitcoin, except maybe to add some like narrow purpose quantum signature kind of opcode. And let's further suppose that you're lucky, and the way the world works is that you can't do covenants on Bitcoin, even given another several years of research. And I don't totally buy that, right? Like I participated with some of you guys at Starkware on this collider VM thing where we showed that like you can collide SHA-1 collision and get covenants on Bitcoin today for like only $100 million of covenant, right? So like, is it never going to get cheaper than $100 million? I think we got it down to 50 actually. Is it never going to get cheaper than that? Okay, maybe it won't. Okay, that's fine. Then okay, that's a stem, and then we shouldn't deploy Simplicity, and then we shouldn't deploy cat, and we shouldn't deploy anything. Okay, but if you accept that we do want to add this extra functionality, if we do want this kind of covenantability, if we want rebindable signatures that we can use for SIGHASH no input, if you want vaults and rate limiting and stuff like this, if you want to define complicated policies that depend on fee rate or that like decay in a smooth way based on age of transactions and stuff like this, then pretty much any extension that adds that functionality is going to enable covenants. It's just, for whatever reason, that the space of possible computations is extremely fragile, and then like as soon as we go a little bit too far, then we just get everything. That just seems to be the case, and we've come very close in Bitcoin's history. We now know that like if we had opcat, right? If of all the opcodes that Satoshi disabled, if cat he had left alone, I think also opmal. There's a couple others like individual opcodes that if he just left them alone, we would have covenants. Like it's super close. if we're going to do that, then wouldn't it be better to do so with simplicity, where people can design systems in a formally specified language, where they're able to reason about stuff, and where they're required to provide all their witness data upfront, and they're required to manage state in ways that are deterministic, and where they have reasoned through all the consequences of reordering their transactions up front, right? That's all. It's not quite the only way. If you really try, you can do simplicity in a super mevy broken way, but you've got to try to do it, and the resulting code will be hard to reason about and broken in other ways, versus a story where we kind of like just ad hoc add some extensions to Bitcoin to enable some specific use cases, and then accidentally, as a consequence, you can like abuse it in this very circuitous way to get these crazy applications. And then the path of least resistance is already so tortured and complicated that there's a good chance that the path of least resistance will be mevy and order dependent and dangerous in these various ways. So that's my view of simplicity, right? Is that if you're not, hardcore ossification forever, then I think simplicity is the way, or something like simplicity is the direction you have to go in to add broad expressivity to Bitcoin.
I think simplicity could be the best path we have at the moment for ossification without creating, risk, right? That because you can extend, you can do a lot of things with it. You can, work around problems. You can adapt to the future. Whereas if you actually ossify today, you're probably going to have a problem, right? Some hash function or signature or something's going to degrade over time, and then you have to take that back and modify it anyway, right? So, and I think ossification is an attractive thing because, gradually making changes sort of introduces a little bit of risk, and as the value goes up, people get more hesitant to make changes. So paradoxically, I sort of think that it might be, because we won't know because it's in the future, right? But it might be less controversial to discuss simplicity than, the ad hoc collection of opcodes. Because, adding opcodes is a bit like the evolution of the x86 CPU set, right? They're adding, new CISC instructions, things that interact with other things. And because we don't get a view inside Intel and AMD where they're fiercely arguing about which opcodes is more important, right? But it's almost the fact that, there could be dozens of different opcodes that could get you to a similar place, and then it's not an easily provable thing which one is better, because it's sort of a program aesthetics. You'll never really know. After you've done it, probably 5 years later, somebody will realize, oh, the other one would have been better after all. We've had stuff like that in Bitcoin before, right? With OP-val and CHV, and so that whole saga. So in a lot of ways, because simplicity is so low level, it doesn't really have a lot of kind of chunky macro arbitrary decisions to make, which is where people get stuck on kind of, sort of circular argument about this opcode's better or that one's better. Well, we don't really know which one's better. Probably won't know for 5 years which one was technically better. I mean, maybe you can prove some of them are just like less expressive or worse, so you probably don't want that one or something. But simplicity takes that all away, right? Because you've got this very low level operators, and you can't like pull one out because then it can't compute things, right? So there's not, and they're very simple, so you can't. There's not a lot of room for design argument about them. It's just like, well, you concatenate 2 bit strings or something super low level like that, right? And so from that point of view, I think simplicity is a good path for ossification, and it takes a lot of the design questions out of it. So it's more permissionless, and it's probably going to be a more dependable and secure script system in a sort of very high assurance context. I mean, Bitcoin script has stood the test of time very well, modulo early issues that got fixed. But I think the formal semantics of simplicity scripts mean that you should be able to have higher assurance that a simplicity, program or verification script that has been had some verifications done on it and some predicates that you care about formally proven. And I think the other thing that we didn't talk about is that the simplicity interpreter itself can also be verified, right? The Bitcoin script interpreter could have some bugs left in it. I think Andrew was hinting that occasionally somebody will find some quirk in it, right, once in a while. But with simplicity, it's tightly enough defined that you can have a proof that the simplicity interpreter correctly interprets all simplicity code, right? So you don't have that with a general interpreter for like RISC-V or EVM or Bitcoin script, right? It's not something easy to do.
Right.
Yeah,
Yeah.
true.
Yeah.
I mean, for STARKs specifically, so simplicity on Bitcoin mainnet would be like the perfect way, because
Absolutely.
it's the cleanest way to bring STARKs, and it will be end-to-end formally proven stack, because we also have like KRO compiler toolchain and the prover proven. So speaking of STARKs, like obviously, so one of the of our goals is to bring Bitcoin rollups with the minimum trust assumptions, but we also can explore in ways we can bring STARKs to different problems in the ecosystem. That's actually how we like simplicity brought our attention. So we just wanted to try, and maybe to just like expand a bit on what STARKs can bring. So Del, if you can just
I will be very quick about that because we don't have a lot of time, and I want you to go through your journey of using simplicity, because I think it's an interesting feedback. So I will be very brief and talk mostly about the use cases that this powerful combination of simplicity and KRO can bring, in my opinion. First of all, I think it can turn liquidity to settlement layer. So you could imagine to build rollups on top of Liquid, or app chains, or interesting applications like a perpetual exchange on top of Liquid. Like think about Hyperliquid, but on top of Liquid. That will be interesting. This kind of stuff, and it's very cool because simplicity is very simple, and you can use Liquid as a settlement layer in a very efficient manner without all the risks that you have if you implement the Stark verifier and your rollup mechanism on a Turing complete virtual machine. So it's more contained, and you have less risks and so on. So it's probably a good place for people to build rollups or app chains on top of Liquid. So maybe you already have some ideas about the kind of use cases that you want to see being built on Liquid with simplicity. But for me, I think it could open the door to this kind of interesting constructions where you can have massive off-chain scaling with execution off-chain. You generate a proof, and then you settle the proof on Liquid, and then you can use the liquidity on Liquid to do some like composability for perpetual exchange or whatever. Yeah, I'm curious if you thought about this kind of use cases going forward. Yeah.
Well, I think it's just that when you see people trying to implement specific advanced things, of course, they can do a little bit more on Liquid because we have checksec from Stack, Cat. We have actually about 30 different helper functions to help serialize things for Covenants. But still, it's a complicated programming model, right? So I think with simplicity, it's just a bit more direct because you're using with kind of macro level opcodes, you're using ingenuity perhaps more, whereas programming should be a little bit more straightforward. I think the other thing that may not be obvious to people listening is that even though simplicity is sort of lower level, like a kind of logic microcode or something, it's still done in a very Bitcoin-like way, which is kind of mind-blowing. That it's you've got the transaction once true remains true, the cachability, the entry into the mempool. So it's in a way, it's kind of like the sort of logical conclusion to Bitcoin scripts, sort of filling in some details below it in a highly consistent way, which doesn't create any surprises or actually makes things more robust, more predictable, more secure, and it doesn't change the programming model, right? Ultimately, it's the assumptions that you get baked into you by programming Bitcoin about how things work, and there are actually, I think, like pretty good reasons for the way they work to do with sort of race condition, avoidance, efficiency, network programming. There's no kind of manual about or design rationale, but if you've done network programming or distributed systems, you can sort of recognize some of these things, or language theory as well. So I think, I think it's actually fits. It's a natural sort of extension to Bitcoin script. I know you think, Andrew, you've been doing advanced Bitcoin script things for years.
Yeah, I mean, there's kind of an interesting bit of history here, right? Because Russell back in 2010, 2011 was talking about MAST, right? With the Merkleized abstract syntax trees, which eventually is what became Taproot, right? Where you've got these multiple scripts and you put them all in a Merkle tree kind of thing. And simplicity kind of came, it was like, what if we took MAST, but instead of just doing MAST for if statements, we like made a whole language that was kind of MASty. That's kind of the evolution of the simplicity language over all these years, right? So yeah, absolutely.
That's cool.
Okay, great. So
yeah,
last thing I want to touch is the simplicity shell, formerly known as Symfony, right? Because it's kind of the entry point for developers that wanted to try this tech right now. And we already mentioned the web interface where you can try it. And yeah, so I also know that there is a community now bootstrapped in various channels, and I already saw a project that compiles Golang to simplicity shell, which is pretty cool. And from just my perspective, I could share that using simplicity shell was kind of like, it's a really fun experience, because you feel really early. There's not much tooling, but it's fairly straightforward to build yourself, and I managed to contribute with some parts of the simplicity stack, and I got a lot of support from Andrew, thanks to you, and Christian and Russell himself. So I think like it's really good stage for developers to tap into simplicity and try to build stuff, because it's pretty powerful. Okay, so I think we can wrap it up. So we don't have many questions, I guess. So thanks a lot for the participants. Thank you, Adam, Andrew, and Del, for the insights and the conversations. Super excited to see simplicity in mainnet. So really hope that one day it will make it to Bitcoin mainnet. So we are on our side. We're continuing working on the Stark verifier in simplicity. So it's now a fully fledged verifier for Stu, our next generation prover. So it's almost there. So we'll be able to prove like a real
meaningful programs, and not only
meaningful, like programs, and it will be on Liquid mainnet soon. So thanks a lot.
Thanks a lot, and congratulations again for the launch, and good luck to bootstrap the ecosystem. I will follow to see the cool applications that people will build with it.
Well, yeah, I mean, I would just say that, you guys taking the initiative without prompting from us to implement a Stark verifier in simplicity is kind of, the canonical power user demonstration, right? It's like, wow, you can actually build a Stark verifier from scratch, and it runs in simplicity, right? People wouldn't expect that's possible, but it shows you can do an enormous number of very flexible things with simplicity, and do it with high assurance, which of course you need for your verifier. And I think there are other uses for simplicity. It's just the formal specification language. Russell was talking about the concept of sort of compiling simplicity into bulletproofs. So you could do it from both sides, right? You could make a simplicity spec, you could compile it into a Starkware proof, and then you could verify the proof with simplicity again. So you have like a Starkware sandwich with simplicity on each side, and it would actually add something. It would make it easier to make formal proofs about the behavior of the Stark things you're verifying in the Stark. So that'd be cool.
Yeah.
All right, Adam's trying to start 10 new conversations here, but unfortunately, I've got a hard stop. So thanks for your congratulations, and congrats to you too for making this Stark verifier. That's super exciting to see. Yeah, that's super cool.
Thank you very
Thanks.
Thank you.
Right.
much. Bye.
Yeah,
Bye.
On this
thanks,
note,
Bye.
let's finish it. Bye
Bye
bye.
bye.
Yeah.
Bye.